I would like first to thank the organizers, and especially Professor Hadley. And he's unfortunately is not. He's already here. Okay. So my talk will be about Monte Carlo pricing of callable derivatives, Bermudian derivatives mainly. So this short overview. Okay, Bermudian derivatives are a special type of options with a special feature of early exercise feature. So early exercise is possible, I assume, on the finite grid of times, capital T0, capital Tj. And a Bermudian option is something between European option and American option, because for European option you have only one possibility of exercise as a maturity time, and for American type option you can exercise at any time before maturity. So Bermudian option is something in between. And these type of options are widely traded. So there are almost all American options are in fact Bermudian options. So we have always a grid of time where the exercise is possible. Apart from the known examples of call-put American options, I will like to give a more interesting example of so-called callable snowball node, which is an interest rate derivative. It pays semi-annually, and at first year it pays one constant rate, constant coupon, and in the subsequent years it pays coupons according to this formula. So it is current coupon is a previous coupon plus A minus LIBOR forward rate. So usually it's 6-month LIBOR forward rate. And the values of A are given in contract. Usually A increases with time. And this snowball node has an early exercise feature, so it can be called at 100% at each payment date. So this is a rather interesting example. This derivative is so rather complicated because we have here dependent on the previous coupon and the special structure of the A, and of course it depends on current forward rate.
So why is it called snowball?
Because you see here this dependence on the previous coupon, then the next depends on the previous one, and so you have some snowballing. And this is a rather interesting derivative, but it's only one example. There are many other very interesting, even more complicated derivatives, which and the pricing of such derivatives is a rather complicated problem, and I will discuss the recent advantages in pricing such type of derivatives. So this is a trading sheet. Here we see the concrete values. So this is a trading sheet from Swiss Bank, Zurich Canton Bank, and here we have 5-year snowball, and here we see the values of A. The A increases, and
But you have to be very close to see it, right?
yes. But okay, it's not so important. You can find it. Unfortunately, it's difficult to increase it, but okay. So now about valuation of such products. So first, let us assume a numeraire. We have a numeraire, and P is the underlying pricing measure, and we define the deflated cash flow, which depends on the underlying process LT, and the price of our option is a solution of the so-called optimal stopping problem. So the price of the option, as is well known, is a C prime over sup over all stopping times belonging to the set from 0 to j with possible stopping possibilities 0 to j, sup of the expected cash flow, deflated cash flow. And this is the optimal stopping problem has been extensively studied in the last 20 years maybe. But here we have some special features that have not been addressed before. These features, first feature is that usually in the case of interest rates we have a highly dimensional underlying process L. For example, in the case of LIBOR models, if we have 40 periods on the semi-annual tenure structure, then we have a dimensionality of 20. And the usual PD methods will not work in this case. I would like to... Yes, of course, because maybe as you know, the optimal stopping problem, the solving of optimal stopping problem usually boils down to the solving of the free boundary problem, the Stefan problem, which is known to be a very difficult problem even in one-dimensional case, not saying about two-dimensional case and the more dimensionality when we have. And the second difficulty is that the deflated cash flow can be path dependent, and this is also what we have seen in the case of snowball node. It is path dependent product. It is not clear how to evaluate this product. And also can be that is only virtually known. So it is known only the sum of some other cash flows. Okay, so I will recall now the main notions from the optimal stopping theory. So first I introduce the Snell envelope process. This is defined inside J. This is a value of option, then has not been exercised before time t, then we can define the current value of option, and this process is a process in time t, a small t, is a called Snell envelope process. And then, okay, this is not a little bit more correct. The Snell envelope process, we have to deflate the current value of contract, and then we get a Snell envelope process, and this is a super martingale. And the solution of the any optimal stopping problem, in particular in our case, is can be found by backward dynamic programming. So we can find the process Snell envelope process by backward procedure. So we put yj equal to deflated cash flow at the last date, and for subsequent dates we put it, we can find our process as a maximum of the cash flow at the current date and the expectation of the Snell envelope process at the future date. So in principle, this problem, the optimal stopping problem, can be solved. But remember that we have the high dimensional problem first, and second that we would like, as a consequence, to use Monte Carlo method. And at first sight, it seems that the Monte Carlo methods are not compatible with the backward nature of the optimal stopping problem, because, as you can see, we have to compute the conditional expectation any time. So we have to simulate trajectories for any time slice. And this leads, obviously, to the nested Monte Carlo simulation. That is quite nasty thing. And it remained an open problem until the seminal work of Longstaff-Schwarz. They have suggested the procedure how to avoid, that avoids nested Monte Carlo simulations. This is picture what I have explained. So we have to simulate at any time, at any point. Since we get the nested Monte Carlo. But first, before I explain the Longstaff-Schwarz procedure, I first introduce another important notion in the theory of in the optimal stopping theory. This is the notion of a stopping family. So we consider the stopping family satisfying this consistency condition. And any stopping family leads to the low bound. This low bound, for the price of the first for the Snell envelope and consequently for the price of the option, can be constructed in this way. So we have to take expectation of the discounted of the cash flow stopped at the according to our stopping family. And then we obviously get a low bound. One possibility to construct low bound, one example, we can define stopping family as the first time we hit a boundary of some domain in the RD. But the most interesting way of constructing low bounds is based on the backward dynamic procedure. So we can try to construct our stopping time in this way that corresponds exactly to our backward dynamic procedure shown before. But here we see that we have to estimate the continuation value. This is this C called continuation value. This is simply expected value of the Snell envelope process. And this is, in fact, again leads to the nested Monte Carlo. But what Longstaff-Schwarz have done, they have suggested not to simulate the new trajectories, but to use only one set of trajectories and compute the approximation of the continuation value using regression. So how does it work? So first this work subsequently. So first we estimate at the last time date we can estimate, because our Snell envelope process is equal cash flow to cash flow at the last date. We can compute the expectation. We can approximately, by using some approximation method, for example regression, then we can get the estimate for the stopping time at time capital J minus 1. Then we again compute the current continuation value. In this way, by using the previously estimated stopping time tau j plus 1. So in this way we can subsequently estimate all stopping value and all continuation values. This is basically the Longstaff-Schwarz procedure, and this procedure has made it possible to compute the price of such Bermudian derivatives or American derivatives without nested Monte Carlo. So basically, Longstaff and Schwarz suggested to approximate at any time step j the continuation value with using regression by choosing some set of basis functions and estimating at any time the coefficients using the sample from Lj z tau j plus 1, where tau j plus 1 again was contracted before.
Your application, how do you choose R?
Yes, this is an important question. So first, here we arrive at two questions and two important problems. First problem, how to choose basis functions, and second, how to assess the quality of the low bound, or equivalently the quality of the stopping time. In my talk, I address the second problem. The first problem I will not address, and maybe I will give some, at the end, remarks how at least it can be approached in practice. So the important question is the policy tau a good one? And the point is that only knowing the low bound, we cannot answer this question, because if we have low bound, this low bound can be very bad, but we don't know the exact value, so we cannot say how far this low bound lies from the true value. What we need an upper bound. And so the rest of my talk will be devoted to several methods of constructing upper bounds. The first very well-known method, this is dual method. So let us consider a discrete martingale, Mj, and construct the bound y0 by this formula. Then it's not difficult to see this is always less than the, if we put the maximum inside, and as we see, this value is always bigger than the y0. And y0, if we take y0 to be Snell envelope, then we get an upper bound here. By its formula, we always can construct an upper bound. And of course, the important question, what martingale does lead to equality? And this is was shown by Rogers and Huff and Kagan, that the optimal martingale can be found from the Dubmeier decomposition of the Snell envelope process. And this, if we put this martingale into our formula for the upper bound, we get the true Snell envelope process. So everything is clear. So we can construct, we have to construct a martingale which is near as much as possible to the true martingale. Another type of upper bound is I call it Rees upper bound, which is also somehow based on the Dubmeier decomposition. So we go from the Dubmeier decomposition, then we use the property that the Snell envelope is equal to the cash flow, deflated cash flow the last time. Then we arrive at this inequality, and finally using this last equality comes from the backward dynamic programming. We get this nice formula. This is a representation for the Snell envelope process. And you can easily see that it's a sum of two terms, and the first term is nothing else than European option, the price of European option. And the second term is sometimes called total consumption. There are different names, so we have called in our paper this is a consumption method, but I would rather prefer risk decomposition because this is exactly risk decomposition. If you look at the in stochastics, it's called risk decomposition. So, but why do we need it? So, what is use of it? It is a very simple observation. If we put instead of y j plus 1 some estimates for y for the Snell envelope process, which is a low estimate, then on the left side we obviously get an upper bound because this term is always positive, so this is minus. So if we put something which is larger than the true Snell envelope process, we get an upper bound. And this leads to the following risk upper bound. So this is if yi is a low approximation, then we get an upper approximation, and then we have this inequality. So this upper bound is different from the dual upper bound and has some advantages over dual upper bound. So the main advantage of this upper bound is monotonicity property. It means that if we have two lower bounds and one lower bound less than another, then for upper bounds we have inverse inequality. So this is very nice property because if you estimate a lower bound with some method, you would like to have this monotonicity property. You would like to see that if you estimated your lower bound better, then you would like to have also the better upper bound. Another property is the locality, that we can use local lower bounds constructed at the given point, and we can take the maximum of these local lower bounds and we get always an upper bound. And we have compared the two different methods, dual and this upper bound, and in fact we can at least construct examples. Then this risk upper bound is better than a dual upper bound and vice versa. So in fact we have to use both. But now I return to the dual method, and I will discuss a procedure for fast estimation of this martingale. This is I have already said, this is a reminder. But in fact, we can find our martingale, dual martingale, by this formula. So what we need, do we need to construct this martingale? So we need to compute here the expectation. If we take a low bound y, we have to compute an expectation, and then we get the martingale difference. But note that in order to compute an upper bound itself, we need then to compute another expectation here. And so we again arrive at the nested Monte Carlo. So in this case, quadratic Monte Carlo, but it's also quite nested. And this is not good, and in recent maybe 5 years, there have been several attempts to solve this problem and to apply some kind of regression method or approximation methods in order to avoid this quadratic Monte Carlo procedure. But this
What is quadratic Monte Carlo?
quadratic is one time nested, so you have here. You have to compute here one time, you have a low bound. Then you have to compute one time expectation here, and then you compute expectation here to get the prices at this is 2. So this is quadratic. And there have been a number of attempts to overcome this difficulty. And but all these attempts were unfortunately unsuccessful because people have always tried to compute, first to get approximation for this continuation value, for this expectation, in such a way that the martingale property is preserved. And this is quite cumbersome. But what we suggest not to estimate separately the continuation value, but estimate from the very beginning the martingale difference. And this can be done using the martingale representation theorem. So first we assume that we are in the Brownian world. So we assume a diffusion process, quadratic diffusion process, and then the following martingale representation theorem holds. And in fact, for any function h, which is such that h of ALT is square integrable, we get a martingale. So this suggests that we can estimate martingale by estimating the function h of this, or equivalently the process h. And after estimating this process, we plug in this martingale representation theorem and get a martingale. And we can expect that if our estimate of h were not bad, then we get also the good approximation for the martingale. But the nice feature is that the martingale property will be preserved.
Why do you know that h is at this point? Yeah.
Because this is, we have assumed here, I have not, this is assumption. This assumption leads also, this is Markov process and Markovian dynamic. So we assume that our process y, but it is usual the case, we can prove it for many interesting examples. So, but this is important, of course. It is that depends on the function h at time t, depends on the current value of the process, underlying process, because later on we will try to estimate it using regression. So the yes, we discretize here. We discretize our, we take a grid such that exercise points belong to this grid. Then we approximate the difference between two values of y. So we approximate this martingale, is integral in the martingale representation theorem. Then they can multiply with a Brownian increment and get the estimate of h. This is a rough idea how to do it. And this idea, I will elaborate it a little bit more later. So, but first we see here that the estimate, of course, depends on the partition of our interval. So the beta partition leads to the beta estimate of h. And upon estimating the process h, we can plug in the estimate in this sum and get the martingale. And what we can prove that this I will give details a little bit later, but now it is now I assume that the expectation here can be computed so directly, without approximation. In this case, we can prove the convergence of the estimated martingale to the true martingale. But now, of course, we don't like to compute the expectation because we would like to avoid the nested Monte Carlo, and so we compute this function h by a regression approach, some kind of regression. So first we choose the basis functions, then we simulate n independent samples from the underlying process. Then we construct the regression matrix and get the estimate of the function h at any point x and the ID.
What kind of basis functions do you recommend?
Yes, we have used polynomials, but it is usual to use polynomials in Lochner-Schwarz method, but I also discuss in my examples what sometimes it is not the optimal way, it's not the optimal choice, because polynomials are increasing, and sometimes we can use damped polynomials, some polynomial multiplied with an exponential function, exponentially decreasing function. But again, I will not address this issue of the choosing a basic function in this talk. But now, finally, we can, upon estimating our martingale, we can plug this martingale into the dual representation and get the upper bound. And this upper bound is obviously a true upper bound because we have a martingale. So this is basically the procedure. Now an example. So we consider max call option on yes.
Do you do regression not in order to get the continuation value that the proxy for the individual?
Martingale, directly for the martingale.
Do you use this you only have two martingale if you use different sample paths for getting these regressors and the integral afterwards.
Yes.
This is what you do.
Yes. We can. And it is important to note we have to use new paths. We simulate new set of paths because we would like to avoid this dependence on because would like to separate the estimating problem and from constructing the upper bound, because they have to be independent, these samples, yes? So we have to simulate one more set. Okay, that's a very simple example, but it shows pretty clear that if we compare our upper bound with the upper bound obtained by Anderson-Brody with the nested quadratic Monte Carlo, we see that the results are almost the same, but the gain in the performance is sometimes even 100% or even more. But here in this example, I can say that we use the same. The Anderson-Brody in their paper have used basis functions based on the European options, which can be computed in this case, or approximately computed. And what we have used for our procedure, we have used the deltas of the European option for the basis function. And that leads to the very nice result. But we also have tested it on the more complicated example, as a snowball example, as I have shown before in the beginning. But then we can use polynomials again, but it is another story how to choose a basis function. And how much time do I have?
10 minutes left.
Okay. Okay, maybe I have a little time to discuss.
Including discussion, right?
Okay,
So
to turn to this, I have still 2 slides, but these 2 slides I would roughly to speak about possibility of dimension reduction in this problem, because it is quite important. If we have dimension more than 20, then we simply cannot use polynomials, or, because then we have to consider all polynomials of 20 variables, a huge number of polynomials. It is not practical. So we have to make some kind of variable selection, or another procedure. I would like to at least to give some hint how to the dimension reduction can be performed in this case. So suppose again that we have the diffusion process. Our underlying process is multi-dimensional diffusion process, and assume that our coefficients are almost affine in the sense that they are given by x multiplied with some small varying vector functions. This is a quite usual case, because maybe you know affine processes are very popular now, but it's not quite affine, but it's almost affine. And in this case, if we assume, for example, the structure of pair function, that the pair function is one-dimensional, and I assume in this case, but it's not necessary that it depends on the some linear combination of the assets. It can be also, in this case, it's a basket option, but we also can consider different type of options. But important is that the pair function is a function to the R, so it is one-dimensional function, and it depends only, it's from R to R. And in this case, using the simple Euler approximation, first order approximation, we can get this formula. And what we can see in this formula is that this is integral, but important to know here that we have here q plus 1 vectors, which define the whole expectation. So we can write this whole expectation, conditional expectation, as a function, some matrix B multiplied with the L. And this matrix B has a rank Q plus 1. And if Q, the number of underlying Brownian motions, was less than the n minus 1, the dimensionality of the process L, then we see the possibility the dimension reduction, because this is we have a very nice form, and this is goes back to the varying coefficients model and single index model, but this is quite, so at least we can approximate this by some kind of model with a low dimensionality. Okay, this is list of papers, and this is, so I think I finished now, yes.
Okay, thank you very much. We have about 5 minutes for questions. Yes, Peter. At some point you will do some multi-housing machines to estimate the quantity which was about H hat, that representation.
Yeah.
If you had a difference quotient there, which from the vertical point of view looks worrisome, because you take differences of small sections of variable motion, right? And then you divide by the time.
Yes, and this is,
how stable is the information?
this is very important question. So we should not take the partition too small, so or too big. So this difference, I'd like to show here. This difference should not be too small, because otherwise we can arrive at problems of stability problems. So this should be some trade-off between the number of paths, the quality of the approximation for expectation, and the difference between 2 points of the partition. So it is, of course, but from our experience, it can be done, and so we have developed some kind of automatic procedure how to choose the partition depending on the number of basis function and the number of Monte Carlo paths. But this is an important problem in practice, of course.
So
Yeah.
analytic result,
What?
We have analytic results.
Analytic results we have also tried, but it's not so easy. We have not yet done it. So we only empirical results, some kind of how to choose H, so the partition size, independence on the number of basis function and so on. So
Another data-driven choice is, of course, this choice of R. I think you didn't answer my question.
what is R?
Okay. You said you will answer it, but it was not answered.
What is R?
Capital R, the
Number of basis functions.
the number of polynomials.
Yes, I would say the most important is even not the number of polynomials, but the polynomial itself or another basis function. So this is crucial issue, but not only for our method, but for Longster-Schwarz method. And
It's an approximation, so you must have some kind of bias with that.
yes, but in this case, here we have a very nice situation. If we compare our situation with situation in statistics, we cannot say if we bias how large bias is biased. But here in this situation, we can always get an upper and low bound and compare them and say that if the upper bound is far away from low bound, we can say this is a bad choice of basis function. So we can always get the output from our procedure, and then we know that we have to improve we have increased the number of basis functions. We should take another basis function. So this is nice feature of this procedure, and that we can always get an output.
But at the end of the day, you have to choose R. Or you just give us a set of intervals of lower and upper bounds.
Yes, we can try to play with R, to increase R, then say, look what happens with upper bound, low bound, and we compare, and we can see.
You see, I'm wrong when I think of the trade-off problem.
Yes, here of course you have a trade-off problem, but you have trade-off problem. The point is, here is a little bit different. It's different from statistic, because if we take a large number of basis functions, you cannot lose. You can it can happen that the upper bound does not improve anymore, but it cannot be.
If you speak about trade-off, it's a trade-off between bias and numerical complexities. Is that a correct statement?
Okay, yeah.
Between bias and variance?
No, I didn't say that.
Yeah, it's just
There's a trade-off. That's why we said trade-off.
point out the difference in statistics.
Yes,
I think the difficulty is to measure the bias, because there is no analytic solution for.
no, but
Maybe I was missing a point, and perhaps you can clarify. So at the beginning you talked about two different ways of obtaining an upper bound. One based on the loop decomposition and one bound on the Rees decomposition.
but this is only for for dual methods. So.
Why did you do this with the Rees decomposition?
Well, it also can be done, but also I have presented it for dual.
Since you mentioned that the Rees decomposition gives you better upper bounds?
Yeah, but if I have said this is sometimes better, sometimes worse, but the advantage is that we have monotonic upper bound. This is the main advantage of Rees upper bound. But okay, it can be also used. This procedure can also be used to approximate to get Rees upper bound. But it is more. It is not so straightforward, because here in the dual upper bound we use directly the martingale, yes, and so we approximate martingale, yes. But in Rees upper bound we don't use directly the martingale. We have to approximate the expectation continuation value. So it is a little bit.
Then you have to do another nested Monte Carlo then.
But what we can do for Rees, we can use this martingale here to construct an estimate with low variance, so as a variance reduction method. But but directly we cannot use here the martingale because the formula is a little bit different. So it's not based on martingale. Yes, it is something different, but it can be also used, the construction of martingale can be used to reduce the variance and the Riesz upper bound.